ठीक आहे, we will start. आवाज येते का माझा? हॅलो
सर खूप हळू आवाज यायले सर.
हळू यायला लागलाय का?
हो खूप हळू यायले.
आता हॅलो
आवाज यायले पण हळू यायले सर.
कोणाला हळू येते म्हणजे सगळ्यांना येते का एक जणाला येते? म्हणजे तुमच्याकडे प्रॉब्लेम आहे का माझ्याकडे कळेल मग?
हळूच येते सर.
हा
हळूच येत आहे सर आवाज.
श्रद्धा आवाज
हळू म्हणजे कमी यायले सर.
कमी येते का?
हो
ठीक आहे, बघू आपण जसं पुढे जाऊ तसं आपल्याला कसा आवाज येतो बघू. सो इन द प्रीवियस लेक्चर इज माय स्क्रीन विजिबल? स्क्रीन दिसते का तुम्हाला?
हो
हा
दिसते
सर
सर.
दिसायले.
So in the previous lecture we discussed about the Maxwell's equations in a microscopic form and a macroscopic form. Now if we consider the Maxwell's equations, we have four things: Gauss law, magnetostatics, Faraday's law, and Ampere's law, and Maxwell's correction to the Ampere's law. Now del dot E is equal to rho divided by epsilon 0. This is the Gauss law in electrostatics. This is a Maxwell's first equation. Del dot B is equal to 0. That is the Gauss law in magnetostatics. This is Maxwell's second equation, which signifies that magnetic monopoles do not exist. Then we have a curl E is equal to minus dou B by dou T. That is nothing but the Faraday's law. That is a changing magnetic field. Changing magnetic field with time produces the electric field. And this is nothing but the Maxwell's third equation. Then we have an Ampere's law. Curl B is equal to mu 0 J. And Maxwell added correction to it. And we have a Maxwell's correction to Ampere's law, or that can be also termed as कोणाचा आवाज येतोय?
सर माझा सर बंद करते सर.
Now curl B is equal to mu 0 J plus dou D by dou T, or curl H is equal, curl B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. Now these are the four Maxwell's equations in the microscopic form. That is, divergence E is equal to rho divided by epsilon 0. Divergence B is equal to 0. Curl is equal to minus dou B by dou T. Curl B is equal to mu 0 J plus epsilon 0 mu 0 dou E by dou T. These are the four Maxwell's equations. It contains the term epsilon 0, that is the permittivity of free space, mu 0, the permeability of free space. When we have the terms mu 0 and epsilon 0 in the equation, in the Maxwell's equation, the Maxwell's equations are termed as a Maxwell's equations in microscopic form. Later on, we defined another two parameters. One is called as a dielectric displacement vector, that is a D is equal to epsilon 0 E, and B is equal to mu 0 H. And when with these substitutions, we have changed the first Maxwell's equation, that is a del dot D is equal to rho. Then we have a second equation as it is, del dot B is equal to 0. Then we have the third equation, curl is equal to minus dou B by dou T. That is also unchanged. But for fourth equation, we have a curl H is equal to J plus JD, or J plus dou D by dou T, where dou D by dou T is equal to JD, is called as a displacement current density. Now these four equations, we have a microscopic form and macroscopic form. Now we are going to proceed further. How the waves behave in one dimension. With this Maxwell's equations, how a electromagnetic wave behaves in a one dimension when it propagates along one dimension. Now see, as I told you, wave. What is a wave? What is a wave? Priyanka brother.
हाँ सर.
What is a wave?
हाँ.
What is a wave? Anybody? Iram? What is a wave? आवाज येतो का माझा?
हा येतोय सर आता.
साळुंके स्नेहा, what is a wave? A wave is nothing but oscillatory disturbance of the medium. When a medium gets oscillated, waves are produced. Now, the wave can be of two types. As already you know, there are two types of waves. One is a longitudinal wave, other is a transverse wave. So the oscillatory disturbance of the medium, for example, I am speaking, my voice reaches towards the microphone. Now here, the oscillatory disturbance of air is produced. Now the oscillatory disturbance of air, that is a compression and rarefactions of air, produces a wave. Now this wave, the wave is traveling along this direction. Compressions and rarefactions are happening along the same direction. Means motion of the particles is along the same direction or in the direction parallel to the direction of a wave. That wave is called as a longitudinal wave. If the motion of the particles or the oscillatory disturbance is in the direction parallel to the direction of a propagation of a wave, we call it as a longitudinal wave. Whereas, if the particles of the medium oscillate perpendicular to the direction of a propagation of a wave, then that wave is called as a transverse wave. See, wave is nothing but an oscillatory disturbance of the medium. When this oscillatory disturbance happens, the particles of the medium can oscillate either in a direction of a wave or in a direction perpendicular to the wave. If the particles of the medium oscillate in a direction parallel to the wave or in the direction of a wave, we call it as a longitudinal wave. So longitudinal wave is sound wave. Whereas if the particles of the medium oscillate in a direction perpendicular to the direction of propagation of a wave, for example, light wave or electromagnetic wave, we have transverse wave. So this is very important. Oscillatory disturbance. If the medium particles of the medium oscillate in a direction parallel to the direction of propagation of a wave, we have a longitudinal wave. If they are perpendicular, we have a transverse wave. In the presence of absorption, the wave will diminish in size as it moves if the medium is a disperse. For example, sound wave. आपण बोलतो, आपण बोललेला आवाज एका रेंज पर्यंत ऐकू जातो, त्या रेंजच्या बाहेर आवाज जातो. Because the medium is absorbed. The medium is absorbed, so therefore the wave gets dissipated. Therefore the wave gets dissipated. Now, if the medium is a dispersive, the different frequencies travel at different speeds. If the medium is a dispersive, the different frequencies travel at different speeds. Now, as an example, let us take an example of a wave with a fixed shape, wave with a fixed shape and constant speed as shown in the figure below. आपण एक दोरी घेतली समजा दोरी आणि दोरी एका टोकाला दोरी बांधली, दुसरं टोक तुमच्या हातामध्ये घेतलं आणि एक त्याला असा जर्क अप्लाय केला आपण, एक वेव्ह तयार होते अशी. ती एक वेव्ह इथे दाखवली आपल्याला डायग्राम मध्ये. So let us take an example of a wave with fixed shape and constant speed as shown in the figure 1. Now this is the position of a wave at time t equal to 0. This is basically f of zt. Now z is nothing but the position. This is along the z axis. And t is the time at which you make the measurement. So this is a wave again. Z is nothing but the position coordinate, and then we have a time t because we make some measurement after some time t. Now let us consider a wave. आतापर्यंत बघितलं आपण. We have wave is nothing but oscillating disturbance of the medium. You have a longitudinal wave and you have a transverse wave. When the particles of the medium oscillate in a direction parallel to the direction of propagation of a wave, we call it as a longitudinal wave. Sound wave is the best example of longitudinal wave. And if the particles of the medium oscillate in a direction perpendicular to the direction of a propagation of a wave, then we call it as a transverse wave. Electromagnetic wave is the best example of electromagnetic wave is the best example of transverse wave. Now, we have considered that when the wave propagates in the medium, for example, मी बोलतो हवेमध्ये, आपण एक समजा बसलो घरामध्ये बोललो, काही ठराविक अंतरापर्यंत जातो. कशामुळे? The wave gets diminished. When the wave gets diminished because of the absorption that happens inside the air. The absorption which happens inside the air. Now, when the wave gets absorbed, its amplitude decreases and we cannot listen to the wave. Whereas for the transverse wave, now, if the medium is a dispersive, different frequencies travel at different speeds. Dispersive असणं म्हणजे काय? जसं तुमच्याकडे एक स्केल आहे, समजा स्केल पट्टी असते आपल्याकडे, रुलर ज्याला म्हणजे आपण त्याच्याकडे बघितलं तर त्याच्या एजला ती छोटी झालेली असते. ती जी एजला छोटी होते दॅट इज अ डिस्पर्सिव्ह मीडियम. दुसरं एक्झाम्पल आहे वॉटर. वॉटर इज ऑल्सो अ डिस्पर्सिव्ह मीडियम. पाण्यामध्ये जर काठी बुडवून ठेवली आपण तर काठी आपल्याला तिरपी दिसते, बेंड होते काठी. That is the example of dispersive medium. Now let us take an example of a wave with a fixed shape traveling at a constant speed. ही wave घेतली आपण. This is the example. This is the position of a wave at time t equal to 0. Initial position. जेव्हा wave start होते, this is the example of wave. When the wave travels for certain time t, if v is the speed, v is the velocity with which, or the speed which the wave is traveling. If the wave travels for certain time t, this t, it will cover this much distance. That is from 0 to the time t. Now let us move further. What happens? What we say? The shape remains same. And I say the wave is propagating. The shape of the wave remains constant, but its position only changes. म्हणजे तुम्हाला उदाहरण सांगितलं मी की एक दोरी घ्यायची, दोरीचं एक टोक बांधायचं एका बाजूला, हँग करायचं, दुसरं टोक हातात घ्यायचं आणि जर्क अप्लाय करायचं असं, विल गेट अ वेव्ह. ती जी वेव्ह आहे त्याचे दिस इज द एक्झाम्पल. This is the position of a wave at time t equal to 0 and this is the position of a wave at time t equal to t. जर समजा आपण if you consider f of z0 is, if you define this by some other function g of z, then we can have g of z is equal to f of z0, or this can be written as a g of z minus vt is equal to f of gt. Here we have written it. If f of zt represents the displacement, that we already. So suppose f of z, g of z is equal to f of z0. Means whatever this point, we have termed this function as a g of z, other function, some other another function. So g of z is equal to f of z0 is the initial shape of the string. Now, at after some time t, he is a second. इथं आपण ह्या f of z0 ला म्हटलं की g of z. After some time t, we have a function f of zt. Now this f of zt can be represented as g of z minus vt. Because this is g of z does not involve any time argument here. So the displacement at a distance vt to the left is at z minus vt. Therefore, we can write g of z is equal to f of z0, and we can write f of z is equal to f of z minus vt 0, or that we can write it as a g z minus vt. This is just a sign convention. This is just a sign convention. Minus vt, the wave, same wave at some earlier time t, because its shape is constant. Now this is the essence of wave motion. Now our main aim is that to study the wave equation in one dimension. How the wave equation can be derived in one dimension. For that purpose, imagine we have a very long string under tension. For example, this is a pen. Let us consider this as a very long string. Now if I apply the tension, if I apply the tension like this, it will bend. I will take a duster. Now if I apply the tension, it will bend, or some other thing also we can take, or some box we will take. Now if I apply the tension, it will bend at two ends like this. Correct? So let us consider a string of some mass. Let us consider a string of some mass m, and that is under the tension T. This is the tension T. आपण जे मी तुम्हाला सांगितलं पेनचं उदाहरण घेऊन, ह्या टोकाला पण प्रेस करायचं तुम्ही, ह्या टोकाला पण प्रेस करायचं. So the pen will bend. It will bend. Now this is shown pictorially or diagram. We have a very long string under tension T, and when we apply a tension T, आता ऍक्च्युअल मध्ये हे स्ट्रेट असायला पाहिजे, सरळ अशी, आणि हे अशी असायला पाहिजे होती. this string is bent due to the tension T. Now आता टेन्शन, सपोज दिस इज खाली आपण प्रेस केलं, आता हा फोर्स आपला खालच्या बाजूने टेन्शन ग्रॅव्हिटी ज्या दिशेमध्ये त्या बाजूने, आपण जेव्हा इकडं याला इकडं करतो, this goes in the upward direction. So याला इकडे केलं तर it goes in the upward direction. So there will be counterbalancing forces in the string. जर तुम्ही इकडे बँड करायला गेला तर इकडे येईल, इकडे करायला गेला तर इकडे येईल. This is called as a counterbalancing of the forces. And when this happens, the net force delta F on this string can be calculated or can be written on the segment Z. This is Z, F against Z. F is nothing but basically some function, and Z is nothing but the coordinate. Now this Z is along this axis, F is along this axis, and if you have a plane, you have Z. We have 2 points, one at Z, other at Z plus delta Z. Now the net transverse force on the segment Z plus delta Z can be written as delta F is equal to T sin theta dash minus T sin theta. So delta F is nothing but the net transverse force. T is nothing but the tension in the string. Theta dash is a very small angle created due to the tension applied to the string. इथला angle at Z plus delta Z. And minus T, again T is a tension in the string. Theta is nothing but this angle at point Z. So the net transverse force of the segment between Z plus delta Z, like this, suppose this pen, if I bend, the net transverse force on this string, that will be delta F is equal to T sin theta dash minus T sin theta. Already I told you theta is the angle of the string. The string makes with the Z direction at point Z plus delta Z. And theta is the corresponding angle at Z. Already we have seen. when this angle is a very small, the tan theta आपण म्हणतो की sin theta divided by cos theta. Now when we consider this as a sin theta as equal to tan theta, means a sin, जर समजा very small angle असेल, 0 असेल समजा, आपण tan theta is equal to sin theta divided by cos theta. आता cos theta cos 0 असेल तर 1 येतो आणि म्हणून sin theta is equal to tan theta. So therefore for very small angles, आता पेन बेंड केला मी तुम्हाला स्ट्रिंग, तुम्हाला याच्यातला अँगल दिसत नाही. How much it has changed? We told. This is a very small angle. Now, as the theta dash and theta are very small, we can replace tan theta with sin theta in this equation. It should be t sin theta minus t sin theta dash minus t sin theta. We can replace this sin theta with tan theta, and we have this equation. It's a tan theta dash. Okay, we can replace it. Just a moment. Here it should be tan theta. Typing error. So we have replaced this sin theta with the tan theta dash. Tan theta dash. आता tan theta म्हणजे काय असतं? Sin theta ला आपण म्हणतो की opposite side divided by diagonal trigonometrically. Cos theta म्हणजे lateral side divided by diagonal. म्हणजे आपण जर समजा एक ट्रायंगल काढला तर sin theta is nothing but opposite side divided by diagonal, समोरची बाजू भागिले कर्ण आपण म्हणतो. And tan theta is nothing but opposite side divided by lateral side. आता इथं जर घेतलं तुम्ही opposite side काय आहे? हा theta angle आहे. Opposite side is a delta f, df. f मध्ये जो चेंज होतो आणि लॅटरल साइड कोणती आहे? झेड मध्ये बदल होणार आहे आणि हे डायगोनल आहे मध्ये. तर म्हणजे f आणि झेड, आणि इथं पण बघितलं थीटा, अपोजिट साइड f आहे आणि लॅटरल साइड जी आहे ती झेड. बरोबर आहे? सो tan theta काढायचं आपल्याला. tan theta इज नथिंग बट अपोजिट साइड डिवाइडेड बाय लॅटरल साइड, म्हणजे समोरची बाजू बघितले लगतची बाजू. आता इथं समोरची काय आहे? df आहे, म्हणून आपण काय केलं इथं df बाय df घेतलं आणि लगतची झेड आहे म्हणून आपण df डिवाइडेड बाय dz, इथं df बाय dz घेतलं. पण कुठल्या पॉइंटला? ऍट z प्लस डेल्टा z. हे दिस इज हॅपनिंग ऍट z प्लस डेल्टा z. बघा लक्षात आलं का तुमच्या? sin theta इज नथिंग बट समोरची बाजू बघितली कर्ण किंवा अपोजिट साइड डिवाइडेड बाय डायगोनल. tan theta इज नथिंग बट अपोजिट साइड डिवाइडेड बाय द लॅटरल साइड. आता आपल्याला इथं tan काढायचं आहे. व्हॉट इज द व्हॅल्यू फॉर tan? सेम इक्वेशन घेतलं आपण, टेन्शन t घेतलं. आता tan theta ला अपोजिट साइड डिवाइडेड बाय लॅटरल साइड, इथं अँगल ला बघितलं अपोजिट साइड इज df, change in f. This is opposite side, change in f, and this is lateral side. This is z. This is change in z, this is change in f. Now this is a dou f divided by dou z, and this happens at z plus delta z. So t tan theta dash, we termed it as this t tan theta dash, we termed as t into the dou f by dou z at z plus delta z. T plus not delta. Here it should be symbolically we can go delta. Sorry. Wait for some time. Similarly, in the similar fashion, we can have at z. Z मध्ये पण काय? हा this is a theta angle. This angle is a theta. This is opposite side. Opposite side मध्ये काय आहे? This is change in f. And this is change in z. So dou f by dou z at z. So dou f by dou z at z. This is the, let us term this as equation number 3. बघा परत लक्षात आलं. We have considered a very long string and applied a tension T. When the tension is applied, the string undergoes bending. For upper side, we have considered the string bends by theta dash. For lower side, we termed it as the string bends by theta. Now the net transverse force we have written as a delta f is equal to t sin theta dash minus t sin theta. Now this theta dash and theta are very small angles, and due to these very small angles we can replace the sine term here and sine term here with tangent. So we have replaced it in equation 2. We have a modified equation. Delta f is equal to t tan theta dash minus t tan theta. Now tan theta is nothing but the opposite side. This is a theta dash, for example. This is opposite side divided by lateral side. So dou f by dou z. So this was a dou f, this was dou z, and at z plus delta z. So we have written this instead of tan theta dash as dou f by dou z at z plus delta z. And for this, we have written this is a dou f by dou z at t. So dou f by dou z at z. Now, up to this it's clear. Now, if a mu we have considered as the mass per unit length of the string. Mu is the mass per unit length of the string. A is acceleration of the element at t. Delta m is the mass of the element. Delta z. Then, according to Newton's second law, F is equal to ma. If mu is the mass per unit length of string, A is acceleration of the element at t, and delta m is the element. हा एक फॉर्म्युला आहे न्यूटन्स लॉ. का F इज इक्वल टू ma असतं. इथं आपलं m हे व्हेरी स्मॉल मास घेतला म्हणून त्याचं व्हेरी डेल्टा m इथं आलं. मग व्हेरी स्मॉल मास असेल तर द फोर्स विल बी ऑल्सो व्हेरी स्मॉल. वी हॅव टर्म्ड इट एज अ डेल्टा F इज इक्वल टू डेल्टा ma. Now we have substituted this one. Delta F is equal to delta m into A. What is a A? A is nothing but the acceleration, which is termed as dou 2f by dou t square. A is nothing but the acceleration, and this is we have termed as a dou 2f by dou t square. So therefore delta F is equal to delta m into dou 2f by dou t square. Now mu we termed as a mass per unit length. Mass काय आपलं? Mass is a delta m. It is mass, and length is a delta z. So mu is delta m divided by delta z. Now, so the value of delta m we have substituted from this mu into delta z. So we have a mu into delta z dou 2f by dou z square. So delta f is equal to mu into delta z into dou 2f by dou t square. Now this is equation number 5. आता बघा. So equation 3, we have a delta f is equal to t into dou f by dou z at z plus delta z minus dou f by dou z at z. And here पण equation बघितलं, delta f is equal to mu into the delta z dou 2f by dou t square. Both are equations for delta f. We can compare. These two equations can be compared together. How it is compared? Let us take RHS of this and compare with this. So we have written it. First we have taken this mu delta z dou 2f by dou t square, and then we have is equal to t into the dou f by dou z plus just a moment z plus delta z minus dou f by dou z at z. Then we have this equation. We can take mu to this side, delta z to this side also. So we have done this. इथं जे mu आहे, mu ला इकडे घेतलं, डिवाइडेड झालं, t divided by mu केलं, delta z total divided केलं आपण याला. So we have this equation. Just I will replace here delta. आता बघा, these two terms we have taken to the right hand side, so it become denominator. T च्या खाली पण इथं t होतं. We have taken it as a mu, and we have the equation. We will make it as a big electrodynamics. So then we have taken the limit. What limit we have taken? Taken limit as delta z goes to 0. That is a delta z is a very small. When delta limit as delta z goes to 0, here to the left hand side we don't have a term in the z, so it will not alter. We'll have the same term as it is, dou 2f by dou t square here. T by mu is a constant, we can take outside, and here we have a delta m, delta z as delta z goes to 0. Here it is remaining. This is a standard definition. If you go by the definition of a limits, as a limit delta z goes to 0, dou f by dou z, delta z minus dou f by z divided by delta z. This is actually the standard definition of dou 2f by dou z square. म्हणजे हे जे काय आहे, this term, this is actually standard definition of dou 2f by dou z square. So we have termed this term as dou 2f by dou z square. We have simplified. आता हे इकडे घेतलंय, म्हणजे dou 2f by dou z square इथंच ठेवलं. Then we have a dou 2f by dou t square. आणि मग mu t घेतलं. Then we have termed this as a v. V is equal to root t divided by mu. इथं आपण सबस्टिट्यूटचा स्क्वेअर केला तर v square is equal to t by mu. आणि मग आपल्याला mu by t आहे म्हणून 1 by v square. We have taken this. आणि मग जर when we rearrange the terms, we have dou to f by dou t square. Here it should be chat. Minus 1 by v square dou to f by dou t square is equal to 0. This is the wave equation in one dimensions. This equation is the wave equation in one dimensions. परत बघा इथून. We have compared this equation is for net transverse force. This is according to Newton's second law. We have substituted the value for acceleration due to gravity due to f by dou. This is a definition. Rate of change of displacement, we call it as a velocity. Rate of change of velocity, we call it as acceleration. Or v is again, when we substitute value for v as a dx by dt or dou f by dou t, the acceleration is a dou to f by dou t square. So delta f is equal to mu into the delta z dou to. We have compared this equation with this equation, and when we compare this, we have this equation. We have taken these two terms to the RHS, simplified. We have taken the limit as delta z goes to 0. We can do it. Delta z goes to 0. We have dou f by dou z goes to this. This is actually the standard definition for. This is standard definition for dou to f by dou z square. आता हे dou 2 by dou z square तसंच ठेवलं, हे इकडे घेतलंय mu by t झाले. We have mu by t dou to f by dou t square, dou to f by dou z square. Let's substitute the value for this mu by t as a, or t by mu as v. So it becomes 1 by v when you make it as a mu by t root, or 1 by v square is the value for this. We have taken this RHS to the LHS. We got this value dou to f by dou z square minus 1 by v square into the dou to f by dou t square is equal to 0. And this equation is called as a wave equation in one dimensions. Like a simple harmonic oscillator equation, this is a wave equation, and this can be applicable to electromagnetic waves or in general any waves. This is regarding the wave equation. Tomorrow we'll have again this wave equation, but for time being, tomorrow I will give you the assignment that you solve this equation. आता जे आपण बघितले ना, तुमच्याकडे बुक्स असतील तर बघा, आणि हे wave in one equation, one dimension, to solve this equation. So what we have learned? We have learned that wave is nothing but the oscillatory disturbance of the medium. If the particles of the medium oscillate in a direction parallel to the direction of propagation, we call it as a longitudinal wave. If the particles of the medium oscillate perpendicular to the wave is going like this and particles are oscillating like this, we call it as a transverse wave. Light wave or electromagnetic wave is the best example of transverse wave. Similarly, sound is the best example of longitudinal wave. Then we have considered the wave, how it propagates. Then we have considered a string, applied the tension, simplified, and we have the wave equation. This is the wave equation dou to f by dou z square minus 1 by v square into dou to f by dou t square is equal to 0. And this is the wave equation in one dimensions. Okay, so for today we'll stop here. I will record your attendance and then we will end the class. So as per rule, switch on your videos. आणि उद्या काय करायचं, म्यूट वर ठेवायचे सगळ्यांनी. एकाने केलं तर बाकीच्यांनी व्हिडिओ ऑन करा म्हणलं तर माईक ऑन करतात. फोटो चांगला आला पाहिजे, पोझिशन मध्ये बसा, असं वगैरे कसं पण बसू नका झोपल्यासारखं. नरी घ्यायचं का?
काय सर?
फोटो
काय?
चांगला आला पाहिजे आपला. आशिष मुळे, किशोर धोत्रे, सोमवंशी, पूजा गंगोत्री, त्यांनी काय दिसूच देणं झालेत आपल्याला. घ्यायचं का? हो का, बाहेर पडले बघा. जस्ट मोमेंट. असाइनमेंट माहिती आहे ना तुम्हाला काय करायचे ते? आता जे क्वेश्चन आपण शिकवलंय ते उद्या सोडवायचं. मी तुम्हाला सकाळी लिंक देईन. त्या लिंकवर तुमच्या वहीत तुमच्या हस्ताक्षरामधलं अपलोड करायचं. क्लिअर? इज इट
Okay.
क्लिअर? गंगोत्री?
Yes. Yes, sir.
गंगोत्री अनम्यूट करावं लागतंय बोलायचं म्हणलं. So we have less than some seconds. Meeting will end automatically. So see you tomorrow. फोटो घ्यायचा राहू द्या, व्हिडिओ राहू द्या चालू. लगेच बंद करते. कसं आहे कॉलेजमध्ये भेटत नाही आपण तर बाकीचे तुमच्या मित्रमैत्रिणींना चांगलं वाटेल ना.